Welcome back. Today, we are going to build the standard atmosphere literally from scratch, deriving the mathematical model from governing physical laws. Our goal is that by the end of this, you won't just memorize a formula. You'll be able to derive, compute, and explain these atmospheric models rigorously. Let's dive in. Here is our roadmap for the lecture. We're going to cover the engineering problem, defining altitude and gravity, the hydrostatic equation, isothermal and gradient layers, a quick numerical application, and finally, model intuition and its limits. All right, part one, the engineering problem. So, you've got flight tests, wind tunnel data, airplane designs, but the real atmosphere, it's constantly changing. Depending on where you are, the time of day, even sunspot activity, the air is in flux. You literally cannot design an aircraft or compare flight performance if your baseline changes every single hour. We need a solid anchor. And we solve this by defining the standard atmosphere. It's a mathematically structured common reference giving us mean values of pressure P, temperature T, and density ρ as functions of altitude. It's built from experimental data and fundamental physics, giving aerospace engineers around the globe a universal baseline to work from. Moving to part two, defining altitude and gravity. Before we touch any equations, we have to strictly define our physical setup. We have geometric altitude, that's hg, which is the literal tape-measured distance from sea level up to your vehicle. But absolute altitude, ha, includes the Earth's radius, denoted by a lowercase r. So ha simply equals hg plus r. Now, based on Newton's law of gravitation, gravity isn't a constant. It actually varies inversely with the square of the distance from Earth's center. The exact formula is local gravity g equals g0 times the square of the quantity r divided by r plus hg. And g0 here is our standard sea-level acceleration of gravity. But doing calculus with a varying g is a massive headache. So we create a mathematically convenient fiction called geopotential altitude, just to note it as h. We define this specifically so we're licensed to assume gravity remains constant at its sea-level value, g0. We force the numerical values of h and hg to represent the exact same pressure changes in the atmosphere, letting us drop that pesky variable g from our integrals entirely. Which brings us to part three, the hydrostatic equation. Let's build our core equation from first principles. Imagine a stationary volume of air in strict equilibrium. The upward pressure force on the bottom face has to perfectly balance the downward pressure force from the top face, plus the downward gravitational weight of the fluid element itself. When we balance those forces, taking the pressure P below, the pressure P plus dP above, and that weight density term, and then apply our geopotential altitude assumption so we can use G0, we arrive at the hydrostatic differential equation. That is, dP equals negative ρ times G0 times dH. Let's define every piece of this explicitly. dP is your infinitesimal pressure change. Rho is the local density. G0 is sea level standard gravity, and dH is the infinitesimal change in geopotential altitude. Pay close attention to that negative sign. It explicitly tells us that pressure must decrease as altitude increases. This equation right here is the foundation for everything that follows. Part 4. Isothermal and gradient layers. Now, physics dictates pressure and density, sure. But temperature? That has to be defined empirically. The keystone of the standard atmosphere model is this experimentally defined temperature variation, broken up into these distinct linear segments. We categorize these segments into two specific types. First, isothermal layers, where the temperature T remains perfectly constant with altitude. And second, gradient layers, where temperature changes linearly. The formula for that is T equals the base temperature T sub 1 plus A multiplied by the quantity H minus H sub 1. That A is what we call the defined lapse rate. To actually anchor this mathematical model, we have to lock in exact standard sea level constants. Vague language is insufficient here. Sea level pressure, P sub s, is exactly 1.01325 times 10 to the 5th newtons per square meter. Density ρ sub s is 1.2250 kilograms per cubic meter. Temperature T sub s is 288.16 kelvins. And the lapse rate A for that first gradient layer, it's negative 0.0065 kelvins per meter. Now for the fun part. To find the pressure in a gradient layer, we walk through this strict calculus progression. Step 1. Start with the hydrostatic equation. Step 2. Divide it by the ideal gas law from prior mechanics. Remember, P equals rho RT, which removes density to yield dP over P equals negative G0 over RT times dH. Step 3. From our gradient temperature definition, we know dH equals dt divided by the lapse rate, A. We substitute that in, setting up an integral from the base temperature T1 to T. Do that integration, and it strictly resolves into this exact full symbolic formula for pressure variation in any gradient layer. The ratio of pressure P to base pressure P1 equals the ratio of temperature T to base temperature T1, all raised to the power of negative G0 divided by the quantity A times R. Let's make absolutely sure every variable is clear before we calculate anything. P and T are the properties at your target geopotential altitude H. P1 and T1 are the properties locked at the base of the current layer. R is the specific gas constant, which is 287 joules per kilogram Kelvin for air. And A is the layer's lapse rate. This beauty right here dictates the precise nonlinear decay of pressure as we climb. All right, part 5, numerical application. Let's plug in some real numbers. Using our exact constants, if we target the top of the first gradient layer, that's a geometric altitude of 11.0 kilometers, the temperature drops to 216.66 kelvins. Run the arithmetic through our derived equation, and it yields precisely 2.26 times 10 to the fourth newtons per square meter of pressure. With this exact method, you can now generate every single pressure value in the standard atmospheric tables yourself. Finally, part 6, model intuition and limits. Now that we have the math, let's build the intuition. Physically, our differential steps showed that the fractional change in pressure with altitude equals negative G0 divided by RT. Look at that denominator, T. In the first gradient layer, temperature decreases as you climb. Because T is getting smaller, the absolute value of that whole fraction gets larger. What does that mean? It means the fractional rate of pressure drop actually accelerates at higher, colder altitudes. But we have to know exactly where our model breaks. This standard explicitly fails if applied above 65 kilometers. Why? Because our foundational assumption that geopotential altitude matches physical geometric altitude diverges by more than 1%. The G0 assumption straight up fails up there. But assuming we stay below that threshold for standard aircraft, what specific aerodynamic lift and drag forces will these standardized densities allow us to calculate next? That is the real engineering power this model unlocks, and exactly what we'll tackle next time.